and I'm here to talk about the non-energy, non-CO2 part of climate change. So even though I did spend actually most of my career in the energy sector. So what inspired this was that there are some really interesting changes happening in the Arctic. In 2017, there was a pilot that was flying over northern Alaska and noticed that there was a lake completely unfrozen, bubbling over with something. A little later that year, a reindeer herder in Siberia heard a very large explosion, and after further investigation, they found these holes like the size of skyscrapers that are peeling all over several peninsulas in the Arctic. So this led to people much more reputable than I am thinking of that there is a really large threat happening from the Arctic on the climate change effect. So what's happening here? The culprit in both of these cases is methane. So methane is responsible for about 20% of global warming. Its concentration is tripled in the atmosphere since prehistoric times. And molecule per molecule, it's 28 times more potent than CO2. The even more concerning part is that there is really a lot of that, like 240 times more of it in the Arctic, frozen in the soils and trapped in various ways than there is in the atmosphere. So this is not like a 1 degree Celsius increase problem. This is potentially 10 degrees Celsius increase problem over some time period. But we don't actually really know what's going on, which is why some of these effects have been very surprising. So just in general, where does methane comes from? The error bars on these things are huge, right? It's very hard to characterize, especially when it's coming out of a large, something like the permafrost, which is 9% of the world's land surface, right? So we have over here oil and gas, which you see a lot of focus on. Very lax regulation is kind of the big problem there. Predominantly methane from cows, where there's a very large number of cows. And here, this is what we're focused on. So this is pretty obscure. This is not wetlands, but other natural methane emissions. And even though the absolute numbers are smaller, the number of these sites and the magnitude of what each site provides is a lot larger. So what we do is we find concentrated methane releases, and then we mitigate them by deploying a small, cheap, durable device that flares the methane, so converts it into CO2, which reduces 96% of the warming for like a very small cost, because burning it is quite easy. We identify the high impact sites, we engineer devices to destroy the methane, a little bit different depending on the geology of the methane releases. We deploy a fleet of them, and then these things are reasonably self-sustaining because of carbon offset markets that are particularly bringing to this problem. So how do we do this? We identify the high impact site through literature review, talking to the reasonably sparse local populations there, and pretty sophisticated satellite imagery analysis of the accompanying visual signals to the methane problem. Detecting methane directly is very hard. What we do is, we come up on one of these lakes that are bubbling with methane. The idea is pretty simple. We put a funnel on it, we then measure it, and burn it, right? In practice, this needs to last a very long time. The methane comes up together with mud and water. It's sometimes inconsistent. The burning needs to be complete. It needs to handle temperatures from like minus 40 Celsius to plus 30 Celsius, high winds, so on and so forth. So in practice, a little more complicated than that, but I'm not any kind of engineer. So here we are in the field, burning some methane. We want to deploy at scale by working with local communities, remote monitoring, and kind of really optimizing the fleet. And the way that the funding of this long term will be through carbon offset markets that are actually are happy to take methane as a greenhouse gas with the about a 25-time multiplier from CO2, right? So for every ton of CO2 that you destroy, you get, let's say, $10. You get $250 for every ton of methane that you burn, right? So this is some of the cheaper ways of addressing climate change. So where we're at, we've identified about 50 metric tons of CO2 equivalents from about 2,000 sources. So that's kind of like in comparison about taking 1 million cars off the roads, but without the kind of economic So it's kind of a much lower friction thing, right? Because we're just like install a thing instead of making a million people figure out how to get to work otherwise. And from an engineering standpoint, we've got a first customer and a first prototype. And these devices are very cheap, right? So at this point we're at about $3,000. The volume's probably cheaper. The deployment is expensive because it's further away. But the carbon offset markets, even for this, like not by far not the best side, we can get 15,000 a year. So as long as we get these devices survive, let's say 10 years in the field, we're talking really good return on investment there. And this is equivalent to like just the amount that we burn out of this like small unoptimized site is the carbon content equivalent, of course not other benefits, of 9 acres of mature tropical forest like per year. So from about a jacuzzi sized thing. So what's next? So we've proven the model. We want to do significantly more satellite imagery analysis to quantify the Arctic potential and figuring out what's happening in the Arctic, increase device lifespan, and then have these certified, have that as a acceptable way of reducing emissions, very similar to landfill flaring, which is already in the market. Yeah, so the dream is that we think we have a cheap and novel way to mitigate climate change, and something that is very motivating for our team, we actually would like to quantify what we think is an existential risk, which is the gases that are coming up from the Arctic. And this is a way to do both. Thanks.